So the first little bit here is just some terminology. So functions of two variables, what they mean when they say that are two independent variables. So technically in these types of functions, you're going to see three variables. But what they mean when they say functions of two variables is two independent variables. So these are like our surfaces. These would create surfaces in 3-space. So we could write them as z equals something with x's and y's, or f of xy equals a function of x and y. So back in algebra, when we first learn about functions, we name the function. We can name it f. We can really name it anything we want. When we first learn about functions, we use f just because it's the first letter of function. And then after the name, in the parentheses, we say what the independent variable is. So for functions of two variables, there are two independent variables. So we have x and y in the parentheses next to the name of the function. So we could either use z or we could use function notation. Z equals the natural of xy, just another example. A function of two independent variables. We get to choose what we plug in for x and y, and then once we plug them in and do the calculation, it spits back a z value for us. So we could write it as z equals, or we could write it in function notation. And since there's two independent variables next to the function name, we indicate what the independent variables are in that function. So it says x comma y next to the function name. We don't always have to use f as the name of a function. Especially if we have a problem that has several functions in it, we don't want them to all have the same name. They need to have different names if they're different functions. So sometimes it'll be a z, sometimes it'll be function notation. But they mean the same thing. So these guys are surfaces in three-dimensional space because there are a total of three variables. The domain, if you think about what domain is back in algebra class, the domain is the set of all the values that we're allowed to plug into the function. Since these functions have two independent variables, we're actually picking two values to plug in. So the domain is going to be a set of ordered pairs. We have to pick an x value and a y value to plug in. So the domain's not a single set of number, it's actually two sets of numbers that go together. So we represent them as ordered pairs. So the domain is the set of all ordered pairs xy for which the function is defined. We only want to plug in numbers for the x and y that give us back a z value or a functional value. And then the range. Do you remember what range is from just pre-calculus algebra? It's usually y values, right?
Y is z.
And right, y is the output in pre-calculus algebra. Here, our output is the z. So just to kind of be more general, in case these variables change, the range is the set of all output values for the functions of two variables. When we know z is always going to be the output, it's going to be the set of z values. But it's just a single set. We only get a single number back when we plug in the two values for x and y. So it's just a single set of real numbers that we get back for f of xy or for z, depending on which format it's written in. So here x and y are the independent variables. And z is the dependent variable. Independent means you're allowed to choose them as long as they're going to give you back a value, as long as it's something valid that we're allowed to plug in to whatever operations are going on in that function, as long as they'll give us back an actual value for z. We don't get to pick the z values. The x and y and then whatever operations are going on determine the z values. So it's dependent upon the x and the y and then the different operations we're going to apply to them. We're also going to see functions of three variables. So that means three independent variables. So that terminology is telling us how many independent variables, not how many total variables we see, but how many independent variables. So these guys, with three independent variables, you're typically going to see x, y, and z as the independent variables. We need a fourth variable to represent the dependent variable, and you're usually going to see w as that fourth dependent variable. So we might see w equals x squared plus y squared plus z squared. It's got four variables in the equation. So if we wanted to write this in function notation, we could say f of, what do you think is going to go in the parentheses? X, y, z. We have three independent variables. We need to list all of them. Equals x squared plus y squared plus z squared. W equals 2xy minus 3y times the sine of xz. Just another example of a function of three variables. On the right-hand side, we see x, y, and z all as independent variables. So we could write it as w equals, or we could write it in function notation. We'd give the function a name, and we would list all of our independent variables in parentheses next to the function. So these would be graphed in four-dimensional space, and we can debate for hours on what exactly that is, but we're not going to. The domain if there are three independent variables, the domain is going to be a set of ordered triples. And the range is exactly the same. If these are functions, you're only allowed to get one output. That's the definition of a function. You're only allowed to get one output. So the range is still just a set of real numbers. So the domain is a set of ordered triples. We've got to pick values for x, y, and z. But the range, there's only one output variable. So there's only one set of numbers for our range. X, Y, and Z are the independent variables. W is the dependent variable. Just going to do a couple quick examples of domain. We're still going to be using all of those same domain rules that we learned in pre-calculus algebra and trigonometry. We reviewed them a little bit when we started talking about domain of a vector valued function. What's going to be a little bit different here is because we've got two independent variables, we're not going to be able to solve for a set of x values and a set of y values individually. Usually what's going to happen is we're just going to be able to come up with a relationship between the x and y values that has to be satisfied. So in that case, we're going to write our domain in set builder notation and just list that rule that we can use all ordered pairs x and y as long as we follow this specific relationship between them. So we're going to use set builder notation to state restrictions on the domain. And the basic setup for our set builder notation is we start with a brace. And for our functions of two variables, we're going to say that we can use all ordered pairs x and y. The vertical line means such that. And then in this spot, we're going to list the restrictions. And then close your brace. So the domain is the set of all x, y such that, and then we list out the restrictions that we have to make sure that we follow. Or if we're doing this for functions of three variables, we would say the domain is the set of all x, y, z, and then we list restrictions. So we're going to do a couple of examples. G of xy is equal to the natural log of the absolute value of x plus y. So what do we need to be careful of when working with natural logs? We can't take the natural log of a negative. We cannot take the natural log of 0. What do you see around the x plus y? absolute values. So we've got absolute values around our x plus y. That fixes the negative part. That fixes the negative part, but it doesn't fix the 0 part. X plus y could still come out to be 0. So we still need to make sure that x plus y doesn't ever come out to be 0. And we need to solve it for one of them. Doesn't really matter which. Y can't be negative x. If y is negative x, when we add them together inside, we're going to get a 0. So if y was 2 and x was negative 2, or if y is 5 and x is negative 5, or if y is 1/3 and x is negative 1/3. So it's an entire list of numbers that's not going to work. Y can't equal negative x. That's the restriction. We have to make sure that our x and y's follow. So we don't want to just say y can't be 5, x can't be negative 5. There are an infinite number of possibilities that go together for the y and the negative x. Okay? So we just have to make sure that we follow that restriction. So we write it in set Boolean notation. So the domain for this function, whose name is g, so we write a little subscript g, capital D subscript g, the domain of g, is the set of all ordered pairs x, y, such that, and we list the restriction that we have to follow. So we'll get an answer back for the output as long as y does not equal negative x. As long as we avoid those, we're good. You just have to remember all that stuff from algebra about these functions. You have to remember that log, we can't do negative or 0. So it's really all that algebra stuff that we need to be careful about. We're going to give a set Boolean notation, but we're going to do a verbal description as well. So f of xyz is the square root of x squared plus y squared plus z squared minus 9. So what do we need to be careful of with square roots? The stuff inside can't be negative. So how can we write that algebraically? So we're going to say that x squared plus y squared plus z squared minus 9 must be greater than or equal to 0. When we're doing square roots, we need to make sure our radicand, which is the stuff under the square root, is greater than or equal to 0. We can do the square root of 0. It's equal to 0. And then we can do the square root of anything positive. So x squared plus y squared plus z squared must be greater than or equal to 9. So we're going to write that in set Boolean notation. The domain for, what do we call this guy? F? X, Y, Z, right. This has got 3 independent variables. It's the set of all x, y, z such that x squared plus y squared plus z squared must be greater than or equal to 9. So we can use all the points for which x squared plus y squared plus z squared is greater than or equal to 9. X squared plus y squared plus z squared equals 9 is a surface in space that we have talked about before, a sphere of radius 3. So x squared plus y squared plus z squared equals 9 is a sphere of radius 3. What does the greater than symbol mean? It means we can use all the points. The equals means we can use all the points on the sphere, and the greater than means we can use all the points outside of the sphere. So at the beginning, Joa said we can't be less than. That means we cannot use the points inside the sphere. But we can use the points on the sphere, and we can use the points outside the sphere. So the equals means it's on the sphere, and then the greater than means outside the sphere. So we can use all points on or outside the sphere centered at the origin of radius.